Hello, we're Team 11, and this is a video about our maze-solving rover. For this project, the rover is expected and designed to navigate freely through a maze while completing the task of searching for a block within the loading zone and then dropping it off at one of the 4 drop-off zones. To accomplish this task, the rover should be able to avoid obstacles, physically transport the load, and achieve localization within the maze. We designed our rover to be compact and simple. It has a rechargeable battery that powers the rover through a DC-DC converter and a separate battery pack the team later added specifically for the pickup mechanism, which is designed to have a high tolerance for positioning error and can operate with only one servo motor and no gears. Processed ultrasonic sensor readings are used for both obstacle avoidance and localization. We decided to include a minimum number of sensors, in this case 5, hoping it would minimize issues later on. Although the localization algorithm through MATLAB histogram is provided, due to some hardware difficulties, the team eventually chose to hard-code the rover routes by taking advantage of its heading direction and the unique maze landscape. The rover would start at a random location, follow the left wall until it arrives at either the unique intersection or the loading zone, its path after which is planned for. Most of the rover's manufacturing process took place in the MIE444 Light Fabrication Center, where team members contributed according to their technical strengths. As it has been shown, our rover did not perform well in milestone 3, specifically after picking up the load. Through rigorous testing, the team identified no logical error in our code. However, there are some limitations inherent to our approach that negatively affected its performance. For example, the rover's identification of loading zone and drop-off zones are heavily relied on its heading, which is updated each time the rover executes a turn function. Here, the sensor readings prompted the rover to do a false left turn, which immediately makes all subsequent planned actions useless even if we put it back into the correct position. We also experienced hardware issues like faulty sensor readings that, despite our best efforts, could not be solved or simply filtered. The fatal problem, though, is how sensitive and different each motor behaves to a changing voltage supply. Since they don't display a particular relationship, our only approach is to constantly test and modify motor speeds, a process which in turn changes the voltage supply, which is really hard to maintain when the team doesn't have a charger. This is also the main problem our rover encountered during the milestone 3 testing. Upon reflection, the team realizes that for projects like this in the future, we should implement a more scientific and systematic approach. For example, testing each component early on and individually prior to integration to identify potential problems, or actually tabulating important statistics. We could also delegate tasks in a more parallel fashion to develop backup solutions. Ultimately, hardware issues are not excuses to poor performances, but difficulties to overcome as in any other engineering projects. This is the end of our video. Thank you for watching.